So we're at the last part of the discussion on garden watering, meaning sort of real fluid flow. Um, Presumably you've done the fourth set of problems, and so remember that the turbulence depends on the Reynolds number. If you've got below Reynolds number of 2300, then you get a laminar flow, so viscosity wins. Above 2300, you get turbulent flow. And so the idea is it depends on the density, depends on the flow speed, and inversely on the viscosity. So if you want a high Reynolds number for turbulence, you get either a high rate of speed or a small amount of viscosity. Either one works. Now, the first question is a kitchen mixer combines the ingredients best when its blades turn fairly rapidly through the batter you're making. If the blades turn too slowly, the various ingredients don't mix thoroughly, even if you wait a considerable amount of time. The advantage of rapid motion of the mixer blades reflects the need for 1. Viscosity to determine the flow of the batter in the mixture so that the resulting laminar flow can fully combine the ingredients. 2. Viscosity dominate the flow of batter in the mixture so that the resulting turbulent flow can fully combine the ingredients. 3. Inertia to dominate the flow of batter in the mixture so that the resulting laminar flow can fully combine the ingredients. 4. Inertia to dominate the flow of the batter in the mixture so that the resulting turbulent flow can fully combine the ingredients. So you either have viscosity, large viscosity to turbulence, or large inertia to give you turbulence. Okay, and so the idea here is that the advantage of moving things rapidly is that basically inertia dominates it. Again, because you get a large velocity, you get a large Reynolds number, and so having turbulent flow means that it'll mix together, fairly well. So remember, with the Reynolds number, if you have velocity on the top, density on the top, then you get high Reynolds number. Viscosity small, you get a high Reynolds number. So, next one. You can add a thickening agent to soup so that the soup becomes more viscous without changing its density. You're stirring 2 pots of soup, one without the thickener and one with the thickener, using identical spoons. You find that the thickened soup becomes turbulent at a lower stirring speed than the unthickened soup. The 2 pots of soup become turbulent at approximately the same stirring speed. 3. The stirring speed has no effect on both pots of soup. They remain laminar at all speeds. 4. The unthickened soup becomes turbulent at a lower stirring speed than the thickened soup. And so again, this is the Reynolds number. Remember, in the numerator, it depends on the density, it depends on the velocity. In the denominator, it depends on the viscosity. So if you have an unthickened soup, then that has you on a small viscosity in the denominator, and so you'll get turbulence at a lower speed. Whereas if you thicken the soup, then the viscosity is larger, and so then naturally you have to get to a higher velocity to get turbulence. So the answer basically is that the unthickened soup becomes turbulent at a lower stirring speed. So it's the fourth one. So the last part of the discussion for this lecture is talking about, why do the pipes rattle when you close the faucet. This is sometimes called water hammer. And the idea is that water, which is moving, it has a density, and so for every volume of water, you've got a mass. And so since it's moving, it also carries a momentum. And so the only way that you can basically transfer the momentum is via impulses, which means a force times the time, as we talked before. So here, though, you're applying a force to the water by changing the pressure. And so it's the pressure times the surface area times the time. So if you have a large momentum transfer, so the water's moving and then suddenly it comes to a stop, then all that momentum has to get transferred someplace, and it does it by basically a pressure impulse. And so you need either large pressures or large surface areas or long times. And so sometimes it's very hard to stop. Remember the demonstration we had where you knock the hammer into the top of the glass bottle. What you find is that essentially the bottom blows out just almost shears off very easily, doesn't break the glass at all. And the reason is that because when you knock the hammer, then the water essentially stays stationary because there's viscosity can't move it suddenly. So the bottle moves, and so essentially, relative to the bottle, the fluid is moving. And so when it needs to come to a stop, then this happens over a very short period of time, and so you need an extremely large pressure, which means a very large force, and it just blows the bottom off the bottle. So the summary about garden watering is that the total energy limits the speed, the height, and the pressure of what comes out of a hose. Bending water flows develop pressure gradients. Nozzles exchange pressure for speed. And the viscosity weights flowing water's total energy, which means that usually that the pressure drops. Turbulence wastes flowing water's total energy as well. So if you have turbulence, that also eats up energy. And this wasted total energy becomes thermal energy. And finally, the moving water has a momentum too. And that's the last bit of the lecture. So we've now pretty much covered everything. This is where we're going to stop. And so this is where the last piece of material that you have for the final exam. So make sure that you do the practice problems. You can find them under final exam practice problems. Look at this review again after you've done the practice problems and reviewed things as much as you can. And then when you're ready, just when you have basically 2.5 hours free, then do the final exam. And remember that the final exam has 100 multiple choice questions. 40 of them will be on stuff that was dates from the midterm, and 60 will be on stuff that was covered after the midterm. So good luck. I'll be in email contact all this week, and I'll be back Tuesday of exam week. So if you have any questions, send them by email or see me when I get back on Tuesday of exam week. The exam will be open beginning probably Thursday morning early of the last week of classes, and it will be open until midnight the last Friday of exam week. One more reminder is that remember that your term papers are due on Wednesday, the last week of classes, and I really have to insist that they be turned in. If you have some disaster, then you might want to give me an email, and I might be able to accept it, give you a little bit more time. But I want the vast majority of the term papers turned in Wednesday by midnight, and I'm going to be sending you lots of reminders. And it has to be then, or else we'll never be able to get them graded in time, because it takes a full solid week to get the term papers graded. So good luck, study well, and hope that this is sort of an unusual way of presenting the material. But let me know by email whether you think this was whether this was a useful way of presenting the materials. This is the first time I've had a lecture that's completely electronic like this. So. It's been good to work with you this quarter, and I hope that you've enjoyed the course. I look forward, perhaps, to seeing some of you again soon. Have a good break.